Great. Well, thank you for coming. I'll be talking about, again, as Paul said, user acceptance issues. I changed the title a bit, but it's still the same idea, looking at designing demand response technology with people in mind. And and this was just working a minute ago. There we go. So I will be talking, maybe repeating a little bit of what Paul just talked about in introducing what is demand response, to talking about some of the problems that we've had electricity that have led to demand response measures being introduced. The bulk of the talk will be about looking at basically the challenges to customer implementation and talking a little bit about some of the work that our group has been doing. So what is the problem? Basically, there is this big problem between energy consumption, electricity consumption, and supply in California. And if you look at some of the statistics, across the U.S., demand has been increasing by about 3% per year over the last 10 to 15 years. And in that same time period, the transmission network is growing by less than half of that rate. In California alone, if you look at the whole .com era, the peak demand, electrical demand, increased by about 18%, and the generating capacity at that same time increased by 0.1%. Okay, so we're looking at this huge imbalance between systems. At one point, the U.S. used to float with about a 20% reserve electrical capacity. Now we're running at less than 10%. So that's led to some of the problems that we're seeing. Many of you have seen this slide before. Basically, it represents the peak demand over the course of a year in California. And so the little sawtooths here represent a week, and then the dips are the weekends. This was represented by most of the commercial electricity use. And you see for bulk of the year, it's right at 33 or so gigawatts. And in the summer, it jumps up here to these peaks, mostly driven by air conditioning loads, both residential and commercial. And then you can see along with that, you get this huge difference in price. Most of the time it's, about average of $30 a megawatt hour, and then it can jump to much more than that. This graph doesn't represent California, but it's very similar to the numbers I've seen from the California utilities. Basically, what we're looking at is, if you look at the cumulative percentage of hours of prices over the course, this is prices for energy over the course of a year, you can see about 5% of the time the prices are extremely high. And then another, 10, 15% of the time, it's above average anyway. And so this led to the utilities having a problem. What are they going to do? Produce a whole new costly power plant just to accommodate this 5% of the year? What are the other issues or some of the other solutions they can look at? Another possibility is to bring up mothballed old fossil fuel generated power plants, which are far less efficient and also produce a lot of air pollution, and they don't comply right now with existing air laws, the requirements for air pollution. And so the solution that a lot of utilities have come up with, and this is actually worldwide, you can see demand response programs in Australia and Europe as well as in the US. This is just being a little sticky today. My next slide shows some of the solutions that led to demand response.
You may have to go to the left.
Okay. Houston, we have a problem. Yeah, the laptop is not advancing either. Mm-hmm.
The laptop itself won't. And the image is there, but if you
Yeah. Response.
If you want, you can take this off really quick, and then you want me to try it? I think it's the laptop.
Okay. And then we exit here.
Okay.
Oh, there we go. Okay.
So I'll
Okay.
plug this back in and try one more.
Apologize for that. So you can see the concern that utilities have is to reduce costs and to hold off building new power plants. And what consumers want is they want reliable power. They don't want brownouts, and they want a stable and reliable, stable costs. And so that's why demand response was implemented, or at least the idea of using demand response. And the goal, again, is to reduce the demand during peak hours, either by shifting or shedding the load. Some of the strategies that are being considered are varying the price, and so actually passing on the real-time price of the cost of electricity to the consumer. There's also load reduction measures as well as demand bidding. I'm mostly going to be talking about the residential aspect of this, which represents about a third of the electrical consumption in California. Demand bidding, for example, is more used with commercial and industrial applications. So that brings up this question of customer implementation challenges. There's a lot of technology.
On the last slide,
Mm-hmm.
could you say what the differences are between those three dynamic pricing mechanisms?
It actually has to do with, in terms of dynamic pricing.
Yeah, the three flavors of it. Could you just say quickly what the difference
Sure, yeah, time of use is basically fairly static rates, so that the price does change, but they're static times that are consistent throughout the year. Real-time pricing has to do with the immediate variable pricing, and critical pricing actually introduces a critical time where it's driven by emergencies and that sort of thing, and so it's an additional variable price rate that changes depending on emergencies. Thanks for that. So part of the challenge here is just looking at the how do we develop the infrastructure that will be necessary in order to implement a demand response, both communication, controls level, metering, and that sort of thing. And the other part is, which I'll be focusing mostly on this talk, is how do you encourage people to participate? And so I'll be looking at some of the challenges there in terms of the big variability, in terms of the end user, a lot of the incentives that are put in place, what drives people to join these programs, and some of the social equity issues, as well as usability and use of the technology. So in terms of the infrastructure itself, how many people are currently working on the DRETD project? Can you just raise your hand, just so people can see in the room? There's quite a few people here that are being funded under this project, and it's basically it's two-year back-to-back contracts with the California Energy Commission, a peer contract, to look at developing these enabling technologies, whether it be metering or modes, communication, the wireless technology, excuse me. I'm also working under a Citrus grant to look at the social implications of demand response. And I'll be talking a little bit about the thermostat control and DREAM system that we've been developing. So going back to the customer participation, there's a huge variability in the end user. Humans are wonderfully erratic in terms of their behavior. You're looking at differences in house size, energy consumption, a number of different things. There was a study done at Princeton a number of years ago that looked at identical houses, identical appliances, and saw 100% difference with respect to energy consumption. So you can see that there's quite a variability there. There's different schedules and so forth. With respect to incentives, this is a major key. Demand response actually requires customer participation. And so that's a big issue here, is how do you encourage people to be involved? And you might think that money might be the biggest driver. There was a study done a number of years ago by a utility looking at solar water heating panels. Why did people put solar water heating panels on their house? And they went through all the different, what they thought might be the different variables. What's the house size, the disposable income of the people in the house, the amount of use, hot water use in the house and people in the household, and so forth. And the number one reason why people put solar water panels on their house is if their neighbor had one. Okay, so we have to look at other issues besides economics in encouraging people to buy into this demand response technology. Other issues such as social equity, people that actually require air conditioning in their home because they're elderly or sick. There's places where there's not a lot of options to electricity, for example, for water heating. People don't have options in certain parts of the planet or parts of the California for that. I'll be talking a lot about the use and usability of this technology as well. So let's jump in here and take a look at This is a list of current demand response programs for residents across the U.S. And this is the major utilities. So there might be some other ones. There might be pilot programs that aren't included here. But these are the major ones. So it's listed by, here's the utility name, the program name, and then the states in which these occur, and then some of the devices that are controlled. Now, of these devices, the majority, I don't know if you can read this in the back here, but a majority of these are air conditioning. So about 19 out of the 23 are really targeting air conditioning, which is a major load. Some are targeting hot water, heat, pool pumps, and then looking at clothes dryers and things like that. So the major electrical loads. What's interesting about these systems, one, I think this one, Xcel Energy here, it's been around since 1990. But what it's doing is it's more, you saw that list of demand response programs I listed at the beginning. One of them was load reduction. Well, most of these are primarily geared towards load reduction. In other words, there's a switch right at the air conditioner that is automatically turning off that air conditioner when demand gets high. It's not related to variable prices at all. But it's somewhat effective. There hasn't been a huge market penetration of these systems in the U.S. They're slowly growing, but it doesn't represent a huge proportion of what's. It hasn't hit a lot of the big percentage of the people that are out there, customers. Jim.
So how do all these systems get the signals to decide what to do?
It really varies. There are, I know one system, I believe, Consolidated Edison, I believe that's through the internet. Most of them are some sort of radio or wireless or pager system. Okay, and there's a huge variation in incentives here too. A lot of these pay people maybe $20 for the year to be involved in this program, or pay them, say, $2 for an event. There's a couple of these programs where you actually have to, the person actually purchases the system. It's actually a lease over a number of years. So after about 10 years or so, you will own the $1,000 system that's in place. That's, I think, the Otter Tail Power system. Gulf Power, I think you actually have to pay $5 a month. And this is the only really true variable price program that's currently out there right now that's not a pilot program.
How do they?
I'm sorry?
How do they get their signal? Is it?
I believe that's also radio of some sort. I don't know. Yeah, I'd have to.
Broadcast radio?
I'm sorry?
Broadcast?
I don't know.
Oh, you don't know.
I'd have to look at the details on that one in particular. This just represents some of the highlights of 3 of these systems. Here's the Good Sense. This is Gulf Power, and you can see that they have this variable price structure. This is Southern California Edison, where you choose up front how much you want to be involved with demand response, whether you want 15 interruptions of your air conditioning or and how much, whether it's off for the whole period or only off for 15 minutes out of 30 minutes. So, and this system down here is up in Montana, and they basically, the system allows you to choose the amount of demand limiting you want. So, but that's the only option. I mean, when the demand goes high, you don't really have a choice about whether you participate or not. It's automatic. You can choose, you can prioritize appliances, but you can't really withdraw at any point.
Can I ask a user issue back? I mean, you've understandably sort of copied and pasted those from some document.
Mm-hmm.
But if I was a brand new user, potential user, where would I go in these 3 cases to get that information?
That's a really good point. All of these are from utilities websites, but I found it very difficult to find this information. I had a list of the programs and what was available, and I did an extensive web search, and it was very difficult. If I were a consumer and just didn't know about the program at all, I wouldn't know about it by going to the website. You really had to dig. I would not know about it in general. You really had to dig to find out where it was. So presumably a lot of these utilities are sending out flyers and so forth to get involved. In fact, Carlos Haid from Southern California Edison said that they sent out 100,000 flyers to get, I think, 1,000 people to participate in the program.
They were delivered to people's U.S. mail boxes?
Presumably, yeah. I believe so. Yes?
Kind of question. Do utilities really care? Or, I mean, are they making more money if we don't observe? Or is it something where the government's forcing them to send us those things to look into their systems?
In terms of these different demand response programs?
Yeah.
I believe that they are, in general, looking at reducing their cost. There's a quote by EPRI, the Electrical Power Research Institute, that showed a study that if you reduce the demand, if you reduce demand at peak times by about 2.5%, you saw a reduction in price by about 24%. And so I do think that that's what's driving utilities at this point. There is some controversy if you look at the literature out there. Some people think that the utilities are just trying to gouge people. But I do think it's driven by their costs and trying to pass their costs on. Yes. Yes. So let's move on here. So the big question, I think, is who is in control? And for the majority of these systems that I just described, the utility is in control. They're actually turning on and off your air conditioner or whatever appliance. And so is this important? I was just at a conference last week where Steve Blank from PG&E said that customers really they actually prefer voluntary programs instead of these restrictive programs. They're doing a number of pilot projects right now, PG&E is. Carlos Haid said that every time an event occurs where they actually turn off someone's air conditioner, they get 10,000 calls from people saying, I want out of this program. This doesn't work for me. Okay. There was a pilot program at San Diego Gas and Electric that showed that 42% of the time the events were overridden, or up to 42% of the time these events were overridden. In that case, people actually did have a choice to override, and they chose to use it nearly half of the time. Okay, so who controls, I think, is actually a pretty big question. There is one of the utilities actually mentions that there's no energy savings, that they actually give a $20 rebate to people that participate. And that, again, is a situation where there's no variable price, right? It's just a load reduction. They're basically assuming that the load is basically shifted. So if you're turning off your air conditioner for a four-hour period, well, you're going to have a rebound effect and the air conditioning is going to come back on. So yet there has not been a lot of evidence that shows there's going to be any reduction in energy savings. There's a number of consumer advocacy group concerns. This is just taken from the TURN website. I don't know if you're familiar with this group, the Utility Reform Network, but this is the headline here is, smart meters, a dumb idea with a high price tag. And so these are some of the complaints that they're suggesting is going to happen if these systems go through, that bills will go up and you're going to have to pay $500 for this new demand response meter and all this, eliminating meter reader jobs and stuff like this. It was actually really interesting that on the same website, they're actually suggested that air conditioning cycling be a better option, which I think is a little bit more Big Brother, because then the user has no control, really. So I thought that was interesting that they are so against these demand response meters. They suggest down here that these systems are only going to be useful for people that have air conditioning, which is about maybe 50% of Californians. And so I wanted to take a look at that. And if you look at this, represents a graph of peak loads in California. And it's hard to read this, but this is residential air conditioning, about 14%. We can also see here that about 6% of that is just miscellaneous appliances. And if you look historically at energy use in the residential sector, miscellaneous appliance is the fastest growing part of that. And that's, if you think about it, look at your cell phones, cordless phones, cameras, PDAs, and all that we're now plugging in. There's just a lot more appliances out there right now than there used to be. This represents a rather fictitious house in Fresno, all-electric home, which is kind of the utility's worst nightmare here. But what it does is it represents, over the course of a day, basically what is the load profile of the energy use in the house, and just listed by the different components, the different appliances. And you can see, to me, this raises a couple of different social equity issues. For example, in the Pacific Northwest, they don't have, or the northwest part of California, excuse me, they don't have access as much to gas. And so you look at some of the appliances here, so they have to use electric clothes dryers, and they have to use electric domestic hot water heaters, or propane, right? But you deal with issues like where these people really don't have a choice about their consumption of electricity. Obviously, people with pools and spas, I suppose they have a little bit more choice, but
the point is they have no choice about using the appliance sometime.
Right.
But they can easily shift the purple and the blue boxes over to 2100 hours there, right? Flat.
They can still shift, yeah, but they still have these appliances. They don't have the choice of moving to gas, whereas most Californians have, I think almost 90% of Californians have, or homes in California have gas water heating, and so it's less of an issue. Okay, if we look at just the housing stock in California currently, about half of the housing stock was built before 1971 and is pretty much uninsulated. Right? You've got some cases where people will go back and add double pane windows or insulate their attic or what have you. And you look at the other end of the spectrum here, and you see only a small percentage, maybe a third of these have air conditioning. If you look at houses that were built in the last 10 years or so, they're pretty well insulated. California has pretty, starting I think 1978 or so, the early 80s, started implementing a lot of energy codes, which have increased every 3 years or so, until you see pretty much better insulation rates or levels recently. But then you look at this trend here. So nearly, 75% of these or so, 80% almost have air conditioning. Now, so has the climate changed in California? All of a sudden it's got warmer and so people need air conditioning? Probably not. One part of it, too, is just I think people are expecting more air conditioning. This also represents a trend that a lot of the new construction in California is happening in the Central Valley, the central areas, which they need more air conditioning. Okay, so I'm going to talk a little bit about, start getting into thermostats. How many people here have actually used the thermostat on the left there? Know how to use it, have used it? Okay, how about the one on the right? Okay, a few less hands. Okay, the Honeywell round thermostat has been around for about 55 years and is pretty well understood by a lot of people. They understand how to use it, but it is what we call a comfort or manual thermostat. It doesn't automatically set back per time of day or anything. It's just the user goes up to it and you change it as needed. These setback thermostats have been required in California new homes since I think about 1978, and the idea was that they are supposed to save energy. The idea is that you set back the temperature in the wintertime, say at night or when you're not at home, or in the summertime you actually set up the temperature again at night or when you're not at home too. And the idea is to save energy. If you look at the challenges of the programmable thermostat just as they are today, well, not everyone has one. Not every home even has a thermostat or a heating or cooling system for that matter in California. A small percentage, but that's still out there. Of the houses, there was a residential appliance survey done in the year 2000 that showed that of the houses that have thermostats, a little less than half of them are programmable. Okay, and this is interesting in that there was fewer houses with programmable thermostats in heating-only areas than there are in cooling areas, which I think is good for demand response. But I think that's again representative of where houses are being built and in hotter climates and having more air conditioning. So the next issue is, do programmable thermostats save energy? And there's actually quite a bit of evidence out there that to suggest that not necessarily. The study in Wisconsin by the Energy Center there showed that it was the occupant's behavior that determined energy savings. So whether or not a person had a programmable thermostat or a manual thermostat, it was due to the occupant's behavior that was so that homeowners that were interested in saving energy set back their thermostats. Didn't matter what technology they had. The Carrier study basically showed, this is a study of 4 different utilities across the U.S., 2 of them were in California, showed that of programmable thermostats that are out there, about half of them are left in hold mode. So only half of them are actually being used as they were intended in the programming mode. There's a couple of other studies that showed, let's say a PG&E study that showed that 2/3 of people in residences continually adjust and reset their systems at any given time. And so they're not using the programming features as much of these systems. So why aren't they being used? I think some of the issues are, there's been a lot of complaints that they're too complex to use. little old ladies are having difficulties with trying to figure out how to use these systems, as well as big strapping adults too. Dick White brought in a 100-page manual about how to use a programmable thermostat at one of our meetings a couple of months ago. I've heard a couple of complaints that they're not flexible enough to accommodate various schedules, right? So people that have variable schedules, they can't program a set schedule to accommodate each day. And there's a lot of people that don't perceive them as necessary. They can use their manual thermostat just fine, and they don't need a programmable thermostat. It doesn't, possibly that it's not flexible enough, or possibly this whole idea of control, that people want to retain control of the system. I threw this in just to show programmable thermostats come with default settings. In fact, to have an Energy Star rated thermostat, it has to come with certain default settings with a 8-degree setback during the night and so forth. But if you look at this was a sociologist interviewing 30 different people in Davis, California, and it just basically asks them, well, what can you tolerate? What's the lowest temperature you can tolerate? Or what's your low ideal temperature? And what's interesting to me is not so much these means are not surprising where they land, but it's the spread that's interesting to me. And so here we have these mandates that say energy, that the default temperature should be X, Y, or Z. But you have, some people saying, oh, well, I can tolerate 50 degrees. Other people saying, I can tolerate 78 as my low. So you really, one size doesn't fit all. We have to find systems that are accommodating people, the variation in people. So I'm going to talk a little bit about the approach that we've been using or designing to try to deal with some of these issues. This is our idea. We call it the DREAM, Demand Response Electrical Appliance Manager. And it's a system of wireless, it's a wireless network of sensors and actuators to be implemented in a house. And the idea is that it's information rich. So it's not only temperature, but look at occupancy sensors and so forth, that you're not just looking at controlling the air conditioning, but also looking at pool pumps and water heaters and so forth. And also looking at power sensing, so actually you can give people information about how much electricity they're using and allow them to set their own schedules and to figure out how they can best reduce electricity consumption. Some of the tasks, I'm not going to list all of these, you can read them, but some of the interesting things we're looking at is, pre-cooling, looking at optimization and whether to use a whole house fan or air conditioning in order to trade off comfort with electricity use. Some learning algorithms to learn parameters. Looking at making the set points maybe a little bit more, developing transients in buildings. And so we're not looking at static set points, but actually set points that move around a little bit and see how that affects people's sense of being in control and also their comfort levels. When I think about actually smart interfaces, I'm actually thinking I should probably rename this as a dumb interface because I want to encourage people to interact with it more. But the idea is that I think the smartest thing in your building is still the person in it. It's not going to be some sort of device out there. And so I want to, the main idea about developing an interface is to try to encourage to use the smarts that are built into that computer and the sensors and the whole network to advise the person, to encourage user empowerment, and to make smarter people. I'm using, this framework is based on David Wyann's 3 I's, and it's looking at how you can balance user participation with control, in control systems, so for better comfort and productivity. And so the first I is insight. Provide insight to the people. Give them information, insight as to how the system works, why they're doing it, what's the reason behind it all. Provide them feedback. How much electricity are you currently using? What's the current price of electricity? And then again, provide them some sort of control, some sort of influence over their own system, so they have actual choices over the amount of their own consumption. They can provide comfort at their whatever they consider to be an affordable price to them. David Wyann. So I'll show you some slides from a prototype of an interface that was developed about a year ago. The idea here is to do something that people all know how to use. People actually, in our usability studies, everyone knew how to operate the thermostat part of this interface. And the other side here is based more on, you've seen this often in web pages and stuff like that, just a kind of a filing system to provide information. So we looked at just how to provide information to people, giving them a sense of a forecast over the course of the day, what the prices are going to be. Give them information such as, hey, if you run your clothes washer here at the high price period, it's going to cost you a lot more than if you do at the low price period. How much have you spent today? So just give people feedback on how much they've spent and what they've spent it on in terms of major appliances. There's a couple different ideas we've had about how to represent a budget, either automatically or just give people information. One idea is that they could type in, hey, I only want to spend $100 this month, and the system would automatically reduce loads and so forth. Or if they want to, just to take a look at, set a target, and then check in every once in a while and see how you're doing compared to that target. This is, again, just showing another way of showing them past usage in terms of the last 30 days, so they can make decisions about, wow, if you really use the air conditioner a lot this month during the high price periods, maybe I could start reducing that, save a little bit more money. And in terms of one of the most difficult things in programmable thermostats is just programming them, just setting up the schedule and the set points. This is still something that we're still working out a lot. Is it's still very difficult for people to come up with these set points. One of the things that we have been looking at is developing learning algorithms. And so you put these systems in people's houses, and they actually learn over the course of time. Oh, this person at such and such time said they wanted to be warmer. Okay, well, let's remember that. Or they want to be cooler, and so forth. The other idea, I was at a conference and saw a thermostat that responded to voice commands. So I think is another idea about usability issues. So for some people, they might feel more comfortable just talking to their thermostat and having it learn that way rather than interacting with them. So in short, our goals are that the system should work right out of the box. It should have a number of built-in defaults that if this system is put into a house, it can carry on its own. It doesn't need any user interaction. It's learning occupant preferences, house parameters. For example, if the house is highly massive or lightweight, has a lot of insulation or nearly no insulation, the system should learn that over a number of cycles. The system should educate and inform people. One of the things that I didn't show on the interface is that we had a series of little video clips that we were planning on implementing that you could show to instruct people. Well, what is demand response? What are all these variable prices about? And so forth. This is how you use a thermostat, and to provide a lot of wizards and things like that to help them through the process of setting up the thermostat itself. Again, trying to make it simple to use, and so that either through following the Honeywell round motif or looking at voice recognition techniques, but trying to make the system as simple to use as possible. And then balancing automatic control, things that the thermostat can actually do pretty well in terms of optimizing a number of different things, with manual control, giving people information, letting them know when's a good time to open up their window or to use their washer or to delay using their washer or dryer because of the price of electricity. To date, we've been doing a lot of work developing the control system as well as the interface through, it's written in Java code, and we've got this sensor and actuator module so we can actually use a simulation tool to see how well our control system is doing. We plan on using this pretty soon to start developing learning algorithms and start testing them. We have a system where we've looked at controlling doing a closed loop in a physical model, sensing temperature, turning on and off the controls. And over the past several months, we've implemented the system in a real house, mostly to look at the network. We are doing a closed loop test of the HVAC controls right now, but we're still having some problems with some of the technology that's available to us. So our next steps, again, are to develop learning algorithms, test the interface and improve it, tie it into the control system, and then test that in a laboratory setting, mostly for usability issues, and then to do some field testing of the whole system in a house, hopefully late this summer. So with that, I'll take any questions or thoughts that you have about what we're doing.